All right, let's talk about entropy. I know, you're probably thinking it's just a fancy word for messiness or disorder, right? Well, what if I told you that simple idea is, well, it's kind of wrong, and that the real story behind entropy is one of the most fundamental, mind-bending rules of the entire universe? Yeah, let's dive in. Think about this for a second. You drop an egg, splat, it shatters everywhere. We've all been there. But have you ever seen that splattered mess just whoosh, put itself back together into a perfect egg? No way, right? It sounds absurd. But why? This isn't just some rule your kitchen follows. It's a law of the cosmos. And believe it or not, entropy is the key to cracking this mystery. Okay, so first up, let's tackle what I'm calling the disorder dilemma. This is the idea of entropy that pretty much everyone starts with. You've definitely seen a picture like this before, right? You've got your nice orderly ice cube, a solid. It melts into a sloshy liquid, and then boils into a chaotic gas. And the story goes, things get messier, entropy goes up. Simple enough. And you know what? That's not totally wrong. But it's like only reading the first chapter of an amazing book. The real reason this happens is so much cooler. So, to really get to the bottom of this, we need to shift our thinking. We're going to move away from this vague idea of messiness and get into something much more concrete. Statistics, probability, and, believe it or not, just counting.
And this right here, this is the game changer. Disorder is a handy little shortcut for sure. But the real deal, entropy, is all about the number of possible ways things can be arranged. The number of configurations. That's the secret.
Okay, so the fancy science word for one of these arrangements is a microstate. Let's make this simple. Imagine you flip, say, 4 coins. One possible microstate, all heads, H. Another one, heads, tails. Each specific combination is its own microstate. Now, scale that up. Think about the trillions upon trillions of air molecules bouncing around in the room you're in right now. The number of possible ways they can be arranged, it's just mind-bogglingly huge. And here it is. This is the equation that was so important, it's literally carved on Ludwig Boltzmann's tombstone. Now don't let the symbols scare you. We only need to care about one letter here, W. That big W is simply the number of microstates we just talked about. It's the count of all the possible ways the system can be. The bigger W gets, the more possibilities there are, and bam, the higher the entropy. It's a beautiful, direct link between pure probability and a law of the universe. Okay, so we've got this idea of counting possibilities. But how does that explain why our poor egg stays broken? Well, it's because this counting leads us straight to one of the most powerful, unbreakable rules in all of physics. Boom, the second law of thermodynamics. All it says is this: if you take a system and seal it off from everything else, what we call an isolated system, its total entropy can never go down. It can stay the same or it can go up, but it will never, ever decrease. This, my friends, is the universe's one-way street. It's the deep reason why time itself seems to have a direction. And here is the absolute key to understanding everything. It's not that the universe wants disorder or likes messiness. It doesn't want anything. Things happen because they are statistically probable. Think about our egg. There is exactly one microstate that we call a whole egg. But a broken egg? Oh my gosh, there are trillions upon trillions of ways the shell bits and yolk and white can be splattered on the floor. The universe isn't trying to break the egg, it's just wandering into the state that has overwhelmingly, ridiculously more possibilities. All right, enough with the theory for a second. Let's bring this down to earth. How does this show up in the world around us? Because once you see it, you'll see it everywhere. Think about it. You drop a sugar cube in your coffee. Why does it dissolve? Because those sugar molecules are going from one single ordered crystal arrangement to zillions of possible places they can be floating around in the coffee. Same with perfume. You spray it in a corner, why does it spread out? Because the molecules have way more options, more microstates available in the whole room than just crammed in that one corner. Ice melting, heat spreading, it's all the same story. The system is just naturally finding its way to the state with the most possibilities. So this chart just lays out what we saw before. Melting and boiling, entropy goes up. But wait a minute, what about condensing or freezing? Entropy goes down. So does your freezer violate a fundamental law of the universe every time you make ice cubes? Is that what's happening? No, of course not. To freeze that water, your freezer has to work. It pumps heat out of the freezer and into your kitchen. That heat energy spreads out among the air molecules in the room, creating way more new microstates out there than the ones you lost in the ice cube. So the local entropy in the ice tray went down, but the total entropy of your kitchen and the universe went up. The law is safe. And this isn't just some abstract idea. It's so fundamental that it's baked right into chemistry. This equation, the Gibbs free energy equation, helps predict if a reaction will just happen on its own. All you need to see is that last part, T times delta S. If that delta S, the change in entropy, is positive, it pushes the whole thing toward happening spontaneously. Why? Because nature loves options. It favors moving toward states with more possibilities. Okay. Let's wrap this up and really cement this new way of thinking. It's time to move beyond chaos and truly redefine entropy. So here's the bottom line. The misconception? Entropy is just chaos or messiness. Let's throw that idea out. The reality? Entropy is a precise measure of how a system's energy is distributed across all its possible microscopic arrangements. It's not about what it looks like, it's about counting the number of ways it can be. And let's lock in these two huge corrections. First, entropy absolutely can decrease locally. Your freezer does it. Life itself does it. It's only possible because entropy increases even more somewhere else to pay for it. And second, something can look perfectly orderly on the outside, like a still glass of water, but be a raging sea of microscopic possibilities on the inside. That water has incredibly high entropy, even though it looks calm. But when you really think about it, entropy isn't just about chemistry or engines or heat. Its reach is so much bigger. It touches the very fabric of reality and our experience of time itself. This is why physicists call entropy the arrow of time. That constant, unstoppable, statistical drift of the entire universe towards states with more possibilities, more microstates, is what makes the future different from the past. It's why we have memories of yesterday but not of tomorrow. It's why broken eggs don't just put themselves back together. So the next time you stir your coffee or watch ice melt, remember what you're really seeing. It's not just messiness. You're witnessing the universe itself unfolding, exploring its infinite possibilities, one statistical step at a time.